Hello, I've been pointing out stupidity and misunderstandings from Flerst in Discord community posts and video comments for a couple of weeks now, and somehow they always come back to misunderstanding how celestial navigation works. Maybe it's time to finally address this. Some needed a kickstart to get to that point, but others went straight for their stupid claim. They are all parroting each other and say that you cannot get an angle from a curved surface. It is kinda sad that they still believe that if you say something enough times over and over again, it will become true. And they still will never show that it actually can't be done. Well, MC Toon shared a video with me where he measured an angle, funny enough, from a curved yoga ball. Yes, Erik Dubé, even a yoga instructor, uses a swear in their profession. But there is a reason why an angle between the direction of a visible horizon and the direction of a star only can be measured from a sphere. And that all has to do with the moment it gets dark. This is a simulation of the sun setting done in Stellarium. After the sun is set, the sky is getting darker and the horizon line is still visible for a while. The most bright stars are now starting to show. These are the stars we do use in celestial navigation and can be found in the almanac. The important stars are visible in the sky and the horizon line is also still visible. This is called the nautical twilight. That's the time when the sun is between 6 and 12 degrees lower than the horizon line. When the sun is passing this and is even lower, the horizon line will not be recognizable anymore against the dark sky, and there will be too many stars visible. This makes it difficult to find the correct stars to do the calculations with. And if you cannot see the horizon line, you cannot even take an angle. This drawing shows the different twilights. Because it shows straight lines, it will be confusing to Flerst.
And now for something completely different.
Let's take an example from Stellarium and draw an angle between stars from a height of 12 meters above the surface, an average height of a vessel's bridge wing above sea level. First we draw the surface and we put a point to measure from, called ground here. Then we take the 12-meter eye height, insert another point as the eye. We look up the distance to the sea horizon in the nautical tables for our eye height. And we got a distance of 7.3 nautical miles. Multiply that by 1852 meters and we have a distance of 13,520 meters. We put the point H on the surface there. And we draw a line from the point I through the point H. We can see it's done from the point we called I. Then a line to the direction of the star. Here we can see the angle is the same as our example. Now you expect that the red line is crossing the blue line at the point H, because the red line is sloping down from the eye height. Now we see it's the opposite, because the blue line is a circle with the radius of Earth and the red line is a tangent on the horizon and is not 90 degrees with our zenith.
And now for something completely different.
For a celestial fix we need, next to the sextant, a clock with the correct time. For the stars a star finder, the nautical almanac of the correct year, the nautical tables or the site reduction tables. Instead of the ABC tables or the site reduction tables, you can also use the formulas or software that uses those formulas. And because we not all carry a globe in our pocket, a dead reckoning position to be able to draw it out on a larger scale. If you do not have a dead reckoning position, you do not belong at sea.
Så hatten af.
Ja, hvorledes?
Efter deres beregning skulle vi befinde os midt i Sankt Peterskirken i Rom.
Ja, så.
De er fyret.
Too bad for you then that the Flat Earth cruise already has been cancelled due to the lack of nautical crew dumb enough to believe in the Flat Earth. But fear not, still there is a way to obtain a dead reckoning position. For the longitude, time the sunset or sunrise. In the almanac you will find the GMT time for the sunrise and sunset at Greenwich, and the change per location go hand in hand with
a 15-degree-per-hour drift.
Thanks, Bob. For the latitude, we take the height of Polaris in the northern hemisphere and the height of the southern rotation point in the southern hemisphere. To find the southern rotation point, we take the line from the southern crux and a line with an angle from 90 degrees from the point between the two pointer stars. Now, where those two lines intersect is the rotation point. We can measure the angle with a sextant, or for a much quicker dead reckoning latitude, we can use our fists. One fist is about 10 degrees. It's not a complete accurate position, but it's good enough for a dead reckoning position to calculate with. And now a message to all flat earthers.
But what I do have are a very particular set of skills. Skills I've acquired over a very long career. Skills that make me a nightmare for people like you.
We definitely don't need that cutscene every time. And yes, we're gonna explain the manual calculation of the globe navigation challenge. For starters, we grab the correct form to keep everything clear. We take the star side reduction form using the artificial horizon because the theodolite up does not need dip correction for an ocean horizon. Now we get a screenshot of the first sighting. Copy the details we need from the screenshot to the form. Name of the star, date, time calculated back to GMT, and the angle measured. Because we don't know the index correction of Michael's phone and the altitude correction is very small, we take the angle measured as the height observed. Let's get the next screenshot and copy the same data. This is the data from Polaris, so we will come back to this. Also here we take the HS as HO. And on to the third screenshot. Copy the same data again. And again take the HO the same as the HS. Now we take the HS from Polaris as the latitude of the dead reckoning position. For the DR longitude, Michael gave us a hint with Central Time or -5. We can simply look that up on a time zone chart. Now choose a nice round number, longitude in the middle of the time zone as a DR longitude. Next, we look up the Greenwich hour angle of Aries on the GMT hour and the date when the measurement was done. All measurements were taken on the 5th hour, so they are all the same. Now we take the correction list of the 22 minutes and find the correction for the 33 seconds. Add those together and you have Aries hour angle for the correct date and time. We look up the sidereal hour angle for Arcturus. And we write down the declination. If we are using the ABC tables or the formula, it's important to write down if the declination is north or south. This is to know later in which sector the bearing is in. Today we are using a program that calculates the azimuth and distance for us on a 360 degree scale. So for us it's only important if the number is negative or positive. Explaining how the ABC tables work will be a 10-minute video on its own. Our longitude is west, so we subtract that from Aries. Now we sum up that angle together with the SHA and we get the local hour angle. Now you can calculate the azimuth with the nautical tables, the side reduction tables or the formulas, but I already said that I'm gonna use an online program. The program will tell us the HC, but it's also possible to get it with the formula. the azimuth is also given in the program, and if the tables are used, is described in a sector. Because the HC is bigger than the HO, I changed the azimuth with 180 degrees to make it more easy to draw. Now we do the same with Polaris. Now the HC is smaller than the HO, we leave the azimuth like this. And we do the same thing again with Procyon. Here the HC is again bigger than the HO, so we change the azimuth 180 degrees again. This is what we get if we draw the azimuths to the stars with the intercept distance of the circle of equal altitude on a map. Now we draw a tangent on 90 degrees on the intercept distance to get the tangent lines on those circles. And I checked my calculations by using the built-in celestial navigation app of the Actis program. First I entered Arcturus, then I filled in the details of Polaris, and as last the data of Procyon. Well, that looks quite similar with the same fix. And here you can see that there actually are. Prototet had the same on his globe. And the winner of the Global Celestial Challenge had it as well with his own written software. And here's the winning answer zoomed out. So, if you want to do celestial navigation with the stars,
this is the way.
This is the way.
This is the way.